Okay. The next talk will be in charge of Dimos Goundaroulis from Baylor College of Medicine in USA. The, the title of the talk is Measuring Distance on the Space of Notoid Diagrams and Application to Protein Folding. Okay.
Thank you, Marcelo, and thanks to the organizers for the invitation. I'm always happy to give talks in this group, and I have a lot of friends there. So yeah, let's start. It's going to be a bit different talk than you guys heard in the previous days. I would like to talk about how we can use all the invariants that we define as knot theorists, algebraists, topologists, and how these invariants and tools that we define get out of the field and they are used into other disciplines, specifically biology, and how these are useful to other scientists, and how we can, make interdisciplinary research using the tools that knot theory produces and algebra produces, and anyway, all of that. So I will start with an overview of the talk. I will give you the basics of the notoid theory, and then I will talk about how we can define open knotting in free space somehow, how we can approach this notion. And we need that because we will study three-dimensional objects like proteins in space, which are, of course, three-dimensional objects. And then we will define two different types of distance, some kind of metrics that we will use those distances to get some information about new biology. So without further ado, I will just start immediately. I will keep the formalism to a low level because I would like to give you more of an overview of the problems and where new theory is needed. Yeah, I will show more pictures than theorems and formalism, but also I will include, of course, formalism because we're mathematicians. So let's start with notoids. So assume that we want to draw a knot diagram, okay? And somehow something happens and we stop midway, so we are left with this open-ended diagram. Now, with this diagram, nothing makes sure that this will remain knotted, because if we start applying any kind of deformation of the curve, some isotropy, plane Reidemeister moves, we can see that very quickly we can undo this open-ended diagram. And of course, what we know from theory, from knot theory, is that we need a closed curve to define a knot. So how we can define some kind of knotting in an open-ended diagram? And now what we will need is to include some kind of restrictions in our rules. And that restrictions are that we don't allow the endpoints of the diagram to cross over or under any other part of the diagram. So having that in mind, we get into this situation. So now we don't allow the endpoints of the diagram to exit this region, and we don't allow this part of the diagram to enter that region. So what we do actually is that we lock the endpoints of the diagram in the regions that they are in. And now somehow we can define what is a notoid diagram. So a notoid diagram is much similar to a knot diagram. It's an immersion of a closed interval now, 0, 1, to an oriented surface. And much similarly to a knot, there are finitely many double points, which are the crossings, and they have information of overpassing and underpassing arcs. And we have also to make sure that this immersion keeps the endpoints mapped somewhere else than the double points. So we cannot map the endpoints of the diagrams on our crossings. That's one restriction. And there is also some convention in the field that we name the image of the 0 of the start of the interval, and we call it the tail of the notoid diagram, and we call the image of 1 at the head of the notoid diagram. And we usually work with two different oriented surfaces, either the sphere S2 or the plane. There are other also surfaces that people want to work with, surfaces with genus, but in our applications, we just stay in these two simple cases, and this is what I will consider for the rest of the talk. Okay, so we can define the regular Reidemeister moves and natoid diagrams as long as we perform them away from the endpoints. We have the forbidden moves that we have always to keep in mind that we respect those moves, so we cannot, again, take the endpoint and cross it over or under any other part of the diagram. And there is an extra move that I always like to consider it as a Reidemeister move 4. This is called the sliding move. We can use it only in S2 for our cases, and it's probably, I mean, someone may say, okay, but this is only an isotopy move on S2, but still, I would like to consider it as a separate Reidemeister move. What the sliding move does is that we can take any arc of the diagram, we can stretch it like here, and we can pass it back on the back part of the sphere. We push it past the point of infinity of the sphere, and we can bring it again from the top, so we can have this situation here where we pulled this part of the natoid diagram around the sphere and we brought it on top, so we can undo this diagram. Okay, so we can always push arcs around the sphere past the point at infinity, and this is also a Reidemeister move for natoids on the sphere. So yeah, given these rules now that we defined so far, it's clear that these two diagrams are not isotopic. So there is no way to go from this guy to this guy and back without violating any of the, the Reidemeister moves and the forbidden moves that we defined. So up until this point. Okay, so having this knowledge, we can go and define what is a natoid. And this was first introduced in the community in 2011 with a paper of Turaev called On Natoids, and it has all of this information now. And natoids, much like knots, they are equivalent classes of natoid diagrams up to the 4 Reidemeister moves, or 3, depending if we work on the sphere or on the plane, and isotopy. Now, some notation here, by K of sigma, we define the set of all natoids on our surface. And if we work on the sphere, this set is a semigroup. We don't have an inverse element. And if we work on the plane, we don't have a multiplication that is not well defined. For more details on all of these facts here, I just cite the Turaev paper for 2011, I think is in Journal of, I think is Osaka, the Osaka Journal of Mathematics. Yeah, so let's continue. And we can say that a natoid, and we will see some examples later, there is a way to go from natoids to knots, to classical knots. So there is always a way to get at most 2 different knots, classical knots, from a natoid diagram. We can get virtual knots, but this is something that I will not discuss about, but there is also a way to go to the virtual case. And this is where people work with surfaces with genus. Now, there is an inclusion map from the set of natoids on the plane to the set of natoids on the sphere, which is of course induced by the inclusion of the plane into the sphere if we consider it as a compactification of the plane, the sphere. And any natoid isotopy class in the sphere can be represented that way by a natoid diagram on the plane. So this, in short, what this sentence says is that if we work with natoids on the sphere, we can just as well draw a natoid on the plane and work with that. This represents very well an isotopy class on the sphere, and we can work quite well with that. Also, there is a map that sends any natoids of the sphere to the plane. This map is well defined. And if we take the composition of the inclusion map and this map rho, we get the identity map, which means that iota is a surjection, it's not an injection. And the reason for that is that we can find several non-trivial planar natoids that become immediately trivial when we look at them as natoids on the sphere. And I will have an example like this in later slides. Okay, so let's discuss how we can get from natoids to knots. First of all, the natural ways, someone will say, okay, connect the endpoints. Okay, so how we connect the endpoints? We have to make a choice. So either we connect with an arc that goes always under, so we have a well-defined operation, so this is the underpass closure, or we go always over. So this is the overpass closure. So this way we can get at most two different knot types from a single knottoid diagram. We can also get different structures in knot theory from a knottoid diagram. We can go to graphs, to specific graphs called theta curves. So theta curve is a graph that has two vertices and three edges. So we can go from a knottoid to a theta curve by introducing two arcs that connects the endpoints. One goes over, one goes under, and we have the knottoid that has been, you see now that this endpoint has been pushed a bit up here. There is a canonical way to go from here to here, but this is not the scope of the talk that I want to focus on. If you guys have a question on how we go from knottoids exactly to the theta curve, we can discuss. But for more information, I just cite the paper by my collaborator Barbensi and her collaborators in 2019 and our joint paper in 2021 for how you can go from a knottoid to a theta curve. And now you can get, it's also well known how you get from theta curves to knots. So you can do a double branch cover of the theta curve as long as you branch over the union of these two curves, okay? So you can go, in the end, you can go from knottoids to theta curves and to theta curves to knots, and you get something close to the overpass on the other, or the underpass closure here. So this is another way to get some closed structure from an open-ended knotted diagram. Another question would be, okay, so all of these are in S3. Can you go in different manifolds? Okay, yes, we can go from knottoids to knots in the solid torus. And the general construction is that, okay, take a disk, cut it open in a specific way, okay, and then take two copies of that and glue it in a coherent way, and then you get an annulus. So you get a knot in the annulus that you can lift into the solid torus, and then you get a unique knot in the solid torus this way. For more information, again, I will just cite you this paper by Barbensi and collaborators from 2018 that exactly describes this operation, how you can go from knottoids on the plane to the solid torus. And why I'm talking all of this, these are the tools that we used to generate all possible knottoid diagrams on the plane and on the sphere and tabulate them, that we will see later. But before talking about the tabulations, someone may say, okay, but can we define invariants on these constructions? And of course, we can extend any known Jones type invariant, any known Vasiliev type invariant to knottoids. So I will just talk about how we can extend the Kaufman bracket polynomial, but everything else is similar. So you just need to make up the rules, to adjust the rules so they include the open-endedness of this diagram. So assuming now that we have a knottoid diagram and we wanna compute the Kaufman bracket, we know that if we have a crossing, we can label opposing regions of the crossing with the same label. So we have here 0 and 0, and then we have the opposing here regions with 1 and 1 labeled. And there are two ways that we can smooth this crossing. We can smooth it one way here by joining the zeros, or we can smooth it the other way. We have an A type and a B type of smoothing, and we can make up a very simple equation here, a scaling relation of the Kaufman bracket, where it says, okay, we have a crossing, so then this is equal A times the A type smoothing, and the inverse, we get the other way of smoothing it. We need also to include a rule that says, okay, if we have the knottoid and a disjoint union of a non-knot, then we can pull out the unknot from the equation and multiply with the factor. And we need also a baseline for our induction, and we give the value of 1 just to the single segment of the knottoid. And that's the difference of the Kaufman bracket on knots from the Kaufman bracket on knottoids. On knots, the induction has a basis of the simple loop. The unknot gets the value of 1. Here, we just change it and we give it to the simple long segment. We give the value of 1. Okay, so let's go and do some computations here. We have this simple natoid that has one crossing here, and we have also a Reidemeister one move here. Okay, so we will see here that we have one crossing, we smooth it one way, we smooth it the other way. Yes, is there a question? Okay, I'm assuming there is no question, and I continue. So we smooth one way, and I smooth the other way, and I make sure that I have the proper coefficients here. And then I have also the Reidemeister one here that I smooth one way the crossing, I smooth the other way. I keep track of my coefficients. I gather together the terms, and we see that, as expected, on the sphere, these two natoids are equivalent because we can apply this Reidemeister 4 move that we said before. Then we can bring this part of the arc on top and then apply a Reidemeister move and untwist this diagram. Okay, so what happens if we worked on the plane? On the plane, if we do the same situation again, we see that we have all of these smoothings, and let's focus here. Okay, we have one situation where the long simple segment here is enclosed in a loop, and here it's outside of the loop. So if we go back to the drawing board here, we just need to add an extra rule. We need to add an extra variable to our Kaufman bracket. We call it now the loop bracket polynomial. And this variable keeps track of how many loops encircle our long segment. Okay, so if I have k loops around the long segment, then this variable will take a power of k. And let's go now and compute again these polynomials. So we will have here a times v plus a minus 1, and this guy will get a different value. Okay, so this now on the plane, we can distinguish these kind of situations. So this is the simplest natoid that we can define with just one crossing, which is quite different from knots because the simplest knot has three crossings here. Okay, so we start to see a lot of variability even for the simplest cases. Now, excuse me, as we said before, we used all of this machinery to create a tabulation of natoids on the plane and on the sphere. And these are the first 10 natoids on the plane. And you see that we have one natoid with one crossing, 6 natoids with 2 crossings. We have more natoids with 3 crossings. I'm just showing the 3 first one. And to summarize, on the plane, we did it with up to 5 crossings. On the sphere, we did it with up to 6 crossings. The classification of natoids on the sphere is complete with for up to 6 crossings. We see that we have a total of 156 natoids. And you can see how much more rich is the situation on the plane. We have 1,137 different natoids on the plane. Okay, think about now how much richer is that. For knots, we have one knot with 3 crossings, one knot with 4 crossings, 2 knots with 5 crossings, and 3 knots with 6 crossings. So it's a lot richer, the information that we take about the topology of these open-ended structures. And this is why they became so useful, and people used it a lot in biology because they showed a lot of variability inside the protein, how the protein is folded. Anyway, people were interested in this variability that we were getting out of that. Now, you notice here that I have an asterisk here. And the asterisk is that in our preprint that we haven't submitted yet, we have a conjecture that these 6 unresolved pairs are different, are actually non-equivalent, because we couldn't find a way to go from one natoid to the other with Reidemeister moves and isotopy. But we didn't develop any theorems to actually prove that, because everybody in the team changed discipline after finishing this project. So everybody worked with something different. So we didn't have time to get back into this. But thankfully, in a recent paper today, this year, well, now it's 23, last year, Maltmaker and Varder Wind defined quantum invariants of natoids, and they managed to show that these two pairs, this guy is different than this one, and this guy is different than this one. So they reduced the pairs of the pairs of our conjectures to 4, which is a huge step forward. So this is what remains to have a complete classification of natoids on the plane. Natoids on the plane with up to 5 crossings. So this is still an open question. People have been tackling it usually with quantum invariants of natoids. They define, all of the machinery that you know from Turaev and Reshtikin. So you can have, all your Hopf algebras and do all of your tensor operations, and then you can define your invariants there, and then you can try and approach and see how you can prove that these pairs are non-isotopic to one another, and that was what Maltmaker and Van der Wien did. This is a great paper. I really liked. I really enjoyed reading that one. So I suggest anyone that's working with quantum invariants to take a look at this. These are very fresh ideas there. I really like them. Anyway, and that's the natoids part. Okay, now we will focus on defining what's an open knot in 3 space. And what we know from topology is that if we have any open-ended curve in space, this is trivial, okay? We can do any kind of ambient isotopy and we can undo this curve. We have 3 different curves here. And from a topologist point of view, as I said, this is trivial, but in applications, people see different levels of knotting here. So for a biologist, this may be more knotted than this guy or this guy. So they will want a way somehow to capture this knottedness and quantify it, get a number, get a polynomial out of it somehow. So what they do is they know, basic knot theory from the 80s and the 90s, and they say, okay, so to get a knot out of that, we just need somehow to connect the endpoints. So there are various ways which are heuristics. There is no clear theory here, okay? This is an open question in the field in math and in protein topology, how we close, what's the best way, the most robust mathematically way to close a curve. And people usually, let's say, okay, there are different ways in the literature. One way is to, okay, let's just connect the endpoints. But connecting the endpoints has sometimes unexpected results. For example, we have something here that looks like a trefoil. If you connect the endpoint with a straight line, you create an unknot. So you get an error. Can you live with that error? In non-precise sciences, they can live. Let's say if I have up to 3% error, I'm okay. If I have a population of 1 million of curves, if 3% of them I get the wrong knot type, I'm okay with that. But for mathematics, we need something better. Another example here is you have a trivial curve. If you connect it, you get a 4-1 knot. And that's a way of the single closure methods. There are several in the literature. I just show you the direct closure one. And from each open curve with the single closure method, that's why they're called single closure, you get one curve out of it. Then there is the other way that it's a bit more robust and a bit more robust to outliers and noise. And this is what's called the multiple closures method. Here, you get all possible closures that you can get of the curve. So with gold color here is the open curve, and with the different colors are all the different closures, well, some of the different closures that you can get out of that. So each color, it gives you a different curve. So gold curve with the blue one is one curve, gold curve with the magenta is another curve that you can get. You get multiple closures, okay? So the idea here is that you go far away from the endpoints and you connect them so you don't interact, you don't create any new crossings. So you somehow capture this. Okay, so the output of that procedure, and this is what usually protein topology people use, this is the method that they use, is a distribution of knot types. And when you want to compute this kind of stuff with the computer, it takes a lot of time. You cannot compute all possible distributions. You want to sample. You want to get a number of them that represents, the population, and anyway, all of these considerations that you have to make. And then you start to measure all the node types in your sample. And the node type that appears most of the times is called predominate, and it represents the distribution that represents your open curve. And this is how people measure noting in biology, okay, and in polymer science and other sciences that use node theory to measure nothing. They usually get the distribution of different node types, and they see which one appears most of the time. And so if you have 80% of the times a trefoil appearing in your distribution, you say, okay, this is a trefoil knotted protein. But these approaches close the curve. We were talking about open knotting. So how would we apply knotoids to this problem? So someone may say, okay, so you have the open-ended curve. Why don't you just project it and you get a knotoid? And I would say, okay, this is a great idea, but what happens if I start to apply, IB and isotopy here? The endpoints will move. So in the projection, the endpoints, I will do forbidden moves in the projection. So I need somehow to fix the endpoints in place. So let's introduce two parallel lines that are perpendicular to the plane of projection, so we can fix in place the endpoints. Now, the whole ensemble has to respect ambient isotopy. What I want to say is that the ambient isotopy cannot cross these infinite lines, okay? So you can define ambient isotopy, but with respect to these two infinite lines, and this is called line isotopy. And you can check the work of Luke Kaufman with Neslihan Gugumtsu. And I think Sofia Labropoulou she had a paper also that introduced the notion of rail knotoids, which is based on the line isotope of knotoids. In any case, introducing these two infinite lines locks the endpoints in position, and you can get a knotoid out of that, okay? So you do that for every possible choice of plane of projection, okay? But the problem now here is that, as you may imagine, is that different choice of projection planes gives us a different knotoid type, okay? So what happens now is that, again, this is probabilistic approach. We get a distribution of knot types. And the way that usually people visualize these knot types, instead of having a huge list of numbers that this is, let's say, 5% trefoil, 1% unknot, is that they consider the curve inside a large enough sphere, and this large enough meaning that is as big, at least, as the convex hull of the curve, and then each pixel of that sphere corresponds to a direction towards which we project the curve. And then we color that pixel according to the knot type, the knotoid type that we get. So then we get these colored globes that look like countries, and the area that the color with the biggest area is the corresponding predominant knotoid type. And this is what represents our distribution. This is the representative of our distribution. Okay, next slide. So we can see, if we spread out the surface of the curve, we can see it a bit better. I have also, I think, something that looks nicer with the choice of colors. So we see something that has a lot of yellow. So this yellow, this knotoid type, is the one that is the predominant one, appears most of the time in the projections, and represents that open curve. So that open curve, I think, is a 6-1. But it doesn't matter. It gives you an idea. You see the color that appears the most, and you check what knotoid corresponds to this color. Now, as I said before, we sample the distribution, okay? So what's the optimal number of projections that we need to sample from that distribution? We have to keep in mind that our computer is limited in the power, in the RAM, everything. So we need to optimize this. And also, if we sample too many projections, the computation of Jones type invariants is a bit heavy. It takes some time to compute. So if you have like 1 million projections, it will never finish. We will be here, we get old, the computer will run. If there is no power break, sometimes we'll finish, but we want something faster. So is there a way that we can define somehow a measure that we can capture the optimal number of projection for a specific protein? Okay, and the assumption that we do here is that all of these moves around the globe are continuous. Okay, so if we move it continuous, the notoid types that will change based on forbidden moves that we introduced in the beginning. Okay, so we are assuming here that neighboring regions of different color differ by a single forbidden move. So now let's define the forbidden distance. So given two notoids, K1 and K2, we define the forbidden distance as the minimal number of forbidden moves across all representatives of K1. So this means that across all the isotopy class of K1 and across all the isotopy of K2, that we need to transform one notoid to the other. So what's the minimum number of forbidden moves that I can do to go from one to the other? And to do that, we need somehow to characterize those moves in terms of their topology, because it seems a bit arbitrary here. So I need to introduce the notion of band surgery here. So if we have like two oriented segments here, I attach a band and I cut it this way, so I get a coherent band attachment here. And coherent means that the orientations are preserved. So it goes like this go like this. So if I attach the band here and I go like this segment, I should have added the arrows, I forgot, I'm sorry. So the orientations are coherent here. And there is also the non-coherent band attachment where there is a twist in the band and the orientations break down. So this is a non-coherent band attachment. So based on that, we have the following theorem. So we use this theorem to characterize all forbidden moves. So if we have two equivalence classes of notoids, K1 and K2, and they are up to rotation and inversion, okay, let's not go into that, but the following three are equivalent. K1 and K2 differ by a single forbidden move, the diagrams, or their corresponding theta curves that we discussed at the beginning, they differ by a strand passage on the blue and the gray edge, or the gray and the red, one of the two combinations, or they're strongly inverted, the corresponding knots. You remember that we can go from theta curves to knots. So they're corresponding knots from the theta curves that they are called strongly invertible. And again, it's not out of scope for this talk, but I suggest that you go to my paper with Agnese here, 2021. So you can see what a strongly invertible knot is. They differ by equivariant band surgery. So equivariant is either coherent or no coherent plus something extra. Okay, some extra information. So now we can see here that the two diagrams, this is the notoid diagram, this is the forbidden move. Now we go to the theta curve. So there is here a passage, a strand passage means that we make a switch of the crossing type. So this is under, we make it over and we move it out. So this is equivalent to that, and this is equivalent to that. And we can see here that from going from theta curves to knots, these two are connected by a single non-coherent band attachment. Okay, we have a twist here. So given this theorem, and what else we did? We did some simulations. So we took all possible notoid diagrams up to 4 crossings, and we computed the forbidden distances that we can do between them. So the simulation on the computer gave us an upper bound on the forbidden distance between two notoids, and the theorem gave us the lower bound. Okay, the computer gave us the lower bound because we did all diagrams up to 4 crossings, and we weren't sure that, for example, let's say this guy here, the forbidden distance between 3,2 and 4,3. There could be, we said that there are between 2 and 3. There could be a non-minimal representation of either one of these two nodes with more crossings. Okay, you may add Reidemeister 1 and 2 moves there, so you create like crossings that are not really contributing to the node type of the notoid, but it increases, the drive of this thing. And we didn't consider that in our simulation. So we needed a theorem to make sure that we have the correct lower bound. So comparing simulations in the computer and the theorem, we came up with a table of the forbidden distances of notoids. Okay. Now the different colors here mean, with blue is if we computed it with coherent band attachments, red is if we computed it with theta curves, and 1 and 2, and the orange, I'm sorry, is that we couldn't find a way to reduce it. We found either 1 and 2 depending on the representative of the curve, so we couldn't somehow get it lower and get a specific number for those. Okay, so the measure that will give us the optimal number of projection, we call it average error. And what we do is that we go back to the globe and these colored countries, and we see how far is the forbidden distance between two neighboring notoids. Okay, the assumption is that the forbidden distance should be always 1. So we count all the differences between those and we take the average. And we see that if we sample 5,000 projections from each globe, or 10,000, we're quite okay. We get an error below 5%, where the field that is interested in that result, biology, for example, they are fine with a 5% error. And also it's quite fast computationally. So this solves the problem of the optimal number of projections. So that's one problem tackled using forbidden distance. This is a metric, okay? It's defined on the space of notoid diagrams. It satisfies all 3 axioms of a metric, and how we can use it in protein science to actually tell people you don't have to sample 1 million projections to see the notoid type of your curve. You just do 5,000 and you can finish in five minutes. Go grab a coffee, it will finish. Okay, so you're done with that. So that's one way. And this appeared in the Proceedings of the Royal Society 2 years ago. And now let's talk a bit how much time I have. I'm almost done, I think, right?
You have
How much?
10 minutes.
10 minutes. Okay, this is great. I don't have many slides left. So let's talk about proteins. So a protein looks like this, okay, more or less. 6% of the proteins, we know that they fold into something that it's knotted. And what is interesting is that the knotting pattern is preserved across species that are separated by many years of evolution, millions of years. So if there is a protein in yeast and a protein in humans, we have the same protein, they have a knot in both organisms, and the knot is the same at the same place. So this suggests that probably there are some advantages that knots give to proteins. And this is an example. So you have this is a different protein. This is a human protein that works very close to the recycling bin of the cells. So there is, when a protein does something, then it gets recycled by this organ that's called proteasome. This protein does something different, but it works very close to the entrance of the recycling bin. Sometimes it gets pulled inside, but it has a knot, and it's a complex knot, a 5-2. So when it's pulled in, the knot is tightening, it blocks the entrance, so it doesn't go in to be recycled. The organ spits it out so it can continue its work. And this is how there are some structural advantages that proteins give to some proteins, because this protein always works. It doesn't get to be recycled that often. So if it gets into the recycle bin, it's a problem. Anyway, so back to the protein, it looks like this. It's very complicated. How do we know if it has a knot? How we can see it? Well, every protein is made of amino acids. Amino acids are letters, more or less like the letters of the DNA. DNA has 4 letters, amino acids are 20. So we have 20 letters. Every amino acid has a central carbon element. If we trace that carbon element, we get a piecewise linear curve. And this is our curve here. It has a trefoil, this one. And we distinguish proteins and to deep and shallow proteins. We have the main part where the knot is happening, which is called the knot core, and we have the two tails, the things that are dangling. And depending on how long these tails are, we classify the protein as deep or shallow. If there is a shallow knotted protein, this means that it's not very stable. The knot may get loosened quite quickly. So what are the different folding ways, how we can actually thread the protein, how they are different? I'm sorry, I got confused here. How different is the folding pattern of a deep protein, a deep knotted protein, and a shallow knotted protein? And this is an interesting question to biologists. So if these ends are long, how different these things are folding? And there are two ways that in the literature now. One way, and that's what's the old, let's say, way of thinking, is that first you have a linear thing because all proteins start like a piece of spaghetti, and then it gets knotted. It starts like this, then you make a loop, and then you thread somehow the loop, and you create your knot here. So you have the single loop way of doing stuff. And the new approach is that there is a theoretical model that says, okay, probably they make two loops instead of one. One loop goes over the other, and then you thread it. But anyway, the main difference is now here that for topologies are the same, they are equivalent, is a geometric difference, one loop versus two loops. But we want to capture this information. Is there a way that we can find this? And there is a paper here by Flappan that appeared in 2019, and she says, okay, this is a topological model of how the two-loop model should be. And she found all these different 8 ways. These are all the 8 possible ways that you can have with the two-loop model, and that's it. There is nothing more. And she characterizes this model with some various structures here, and she has like 2 letters that indicates, as you can see, we have 4 colors here: green, red, blue, and black. So the L, the 2 L's or R's here, it indicates if the left part or the right part of the red and the green is over the blue one. So here we have LL because the green is over the blue one, the left part of the green is over, and the left part of the red is over the blue. Then you have a positive here for the sign of this crossing, and you have AB with a number of twists. Okay. So now we want to capture all of this information, topological information, geometric information. So to use that, we use the statistical distance of Earth movers distance, and this is our contribution here in this field. So assume you have 2 finite discrete distributions, and each point in this distribution has a weight, and assume that you have a matrix that you convert one distribution to the other, can be any matrix in the M times N space. Then you can define this sum we call work, and you can weigh and then you can find the minimum work that you need to go from one distribution to the other, and you average it over the weights. Anyway, this is easier to show than explain. If you have one distribution here and another distribution here, what's the minimum cost that you have to pay to change the bars from the left one to the right one? How you can move the bars up and down, or take some of this bar, put it to the other one, so you can match the 2 distributions. Now, if we take the distributions X and Y to be natoid distributions, and the weights to be the forbidden distance of every natoid in each individual distribution from the trivial natoid, and this should be, the trivial natoid, not 0, 1. First, okay, let me jump this. You can somehow tell the differences between the folding patterns of the deep notoids, the deep folded proteins, and the shallow knotted proteins. In this experiment, what we did, we took all these 8 different models that Flapan said, and we generated all possible combinations. We generated artificial curves with this, random curves, a large number of curves. And then we analyzed the notoid pattern for each one of those. And then we took all trefoil knotted proteins and we mapped them together. And we tried to see how they cluster together. So there are 2 interesting results here. And I'm going too fast, but I don't think I have much time. So first of all, the blue one here is the old model, let's say with a single loop. Everything else are the new models with the 2 loops. All deeply knotted proteins, that's a new result. They follow the path of the single looped model. And there is a small family of shallow knotted proteins that people didn't know that fold with 2 loops. And that's the main result. This is what we contributed to that. So what we did was to take topological and geometric information of each curve and somehow, use it to give information about biology of proteins. So this was something that biologists seem it's interesting to them, so they somehow used that. And I will just, Here we confirmed our results with some simulations. So we took random polymers and we folded them according to the rules that follow for protein folding, and we confirmed our experiment about what we did. And most of this job, at least at the beginning, this is at the end of the talk, was done in Switzerland with my boss, Andrzej Stasiak, and my collaborators, Julien and Fabrizio. And the last part with folding mechanisms was done with this group of, now they are all PhD, they got their PhDs, most of them are postdocs, or some of them they are in left academia, they are in industry, but these are all the people that work in this big project. And I would like to thank all of you for your attention, for your time here, and for the interest in showing in this talk. Thank you.
Thanks, Dimos, for your talk. Is there any?
I have a couple of questions, please. So first of all, Dimos, thank you so much for your interesting talk. So that's really, really beautiful to see all your pictures.
Thanks.
So at the beginning of your talk, you mentioned a semi-group on the sphere, but
Yeah.
I didn't get the product in that semi-group.
Oh, okay. I mean, the product is very well defined. I think is section 7 of Turaev's paper. You just it's somehow a controlled way of joining the endpoints of the natoid somehow. You don't cut, you don't do any kind of cutting and pasting, but there is a canonical way of joining the endpoints.
I see.
But there is no inverse in that. I think it's section 7 or section 8. I'm not, it's been a while since I read that paper, but it's the Osaka Journal 2011 Turaev paper. It has all the information there.
Okay, so my second question is do you have an algebraic description of this kind of object?
Of natoids?
Yeah.
So this is an open question. People try to do braidoids. Sophia Labropoulou, my supervisor, my PhD supervisor, tried to do some kind of algebraic formulation of that. From what I remember, it's been a while since I saw that, you cannot even get them into a monoid structure there. So it's open. The field is open there. I mean,
I see.
Still people work on that.
And so that was my few questions. So what is the relation between the notoids and the braidoids? Because, for instance, when you have the classical nodes,
Yeah.
So you can in some sense, it's very intuitive to get a braid, right? But here I cannot see how it's possible to do that.
How you go from braidoid to knotoid? How you
Yeah,
braid?
for instance.
I'm not sure. I don't remember honestly. I cannot give you a straight answer now. But I remember that Sophia was having a certain number of assumptions before joining, the strands of the braidoid, because she had always two strands that were never connected because these corresponded to the endpoints, and then there was a somehow canonical way of joining everything else in the braidoid, all the other strands of the braid, to get the knotoid. But I don't remember now I don't remember the actions for that. Sorry, but she has a paper on symmetry, I think, on braidoids.
Okay, so my last question is if in one slide I didn't get as well. So could you explain the notion of stability that you mentioned when you enter in the protein part?
Yes. Can you be a bit more specific?
In
Because
one moment, you mentioned that a notion of stability for the knotoids. So, but I didn't get. So what that means
do you
about?
mean that with the change of projections we get a different knotoid type? This was
Yeah, exactly.
Okay. So let's get back to the maybe it was too fast. It's true. So you're talking about this part that if we project this way, and then we project that way, and then we project that way, we get different knotoid diagrams. You see here, you get something that has one crossing. You get something that has two crossings here, and you get something that has two crossings here. These two projections here on the left and on the bottom, they are equivalent, but this guy here on this wall, it has one crossing. So you need somehow to make up for this. And to make up for this, you get actually how you make up is you consider everything. You say, I have a distribution, I don't have a single knotoid type. I have a distribution of all the knotoid types, and then I see which one appears most often.
I see.
So in this case, for example, we had three projections, so our distribution was, we got two different these two walls have the same knotoid, and this guy has a different knotoid. So our distribution had two knotoid types, and since the knotoid with the two crossings appear most of the times, we say, okay, this is this guy here, 2-1. This is a 2-1 knotoid that represents the whole distribution, and the distribution represents the whole the curve.
Okay, so thank you for your answers, and thank you for the.
I hope it was clear. I hope and I hope it was interesting for people. These are the ways that, I mean, the tools that people outside of math and topology use are simpler than the ones that we construct, but nevertheless, they are very interested in what we can give them to use. So this is an open field, let's say, for all of us to consider, how we can reach out and show other disciplines, how they can use our tools and make them, let's say, also computable, easier, let's say. That's my experience, at least. Thank you so much.
Dimos, there is another question here in the public.
Yes.
Thanks for your talk. I really enjoyed it. I have a question. So there is like a motivation for the existence of a method, downtown theory. For example, you're talking about C0, but just continue.
I'm sorry, I cannot hear you very well. Actually, I cannot hear you at all. Could you get?
Is there any motivation for a theory, for a metric non-toy theory? I mean, the necessity of finding minimizers in spaces of non-toys. For example, we could do it in the space of diagrams or in three-dimensional. Of course, we have to give some extra conditions of the regularity of the curves. But my question is, Is there any biological motivation for that?
Biological motivation to define the distance?
Well, but I'm talking about given one notoid, or is there a necessity of finding a minimizer in this class? For example, when we study physical knots, we have the triple knot, right? So we have a knot with a similar neighborhood, right?
Yes.
You want to shrink it so that you get the minimum. And we
Oh,
know
I
that-
see. Yeah. So this is called ideal knots.
Exactly. Well, yes, ideal knot, physical knot.
And yeah, so this was introduced by my boss in Switzerland, actually, Andre Stajek. So what they wanted to do, they wanted to, their physical, I'm sorry, yeah, I got distracted by a phone call. The biological question, yeah, all these knots that you can see, not in protein, but mainly in DNA and in circular DNA, they are, oh man, they are calling me anyway. In circular DNA, they are tight. So you need to, how can I say it in plain terms now? Okay, so you need an invariant, a physical invariant to tell you what kind of knot you have because they are very tight. That was the minimizer approach. So yeah, it was mainly based on experiments because biologists, they have, let's say, their own knot invariants. They have a gel, let's say, they have a machine that you put your DNAs there and you see how they run in the gel, and then you can say, it stayed on top, this is a unknot, it went below, it's a trefoil. So now how we can take this and quantify it into a number? So they took that and they made the physical knot, because how tight is knotted that DNA circle, it makes it travel faster in that gel. So yeah, there is a biological need there. It was in the 80s, no, 80s, it was developed in the mid 90s. But yeah, other than that, I'm not aware of anything else. Maybe in polymer science that I haven't talked recently with any people there. They would be interested in minimizing these open knotted curves. But for closed curves, there was a need to know, to quantify this movement in that gel surface. This gel electrophoresis is called. This movement there, and it appears to be in the end a numerical knot invariant, which was great. I hope this answers your question. If I understood.
Yeah, partially. I mean, the things you mentioned, I heard about them. And actually, I'm going to talk about this stuff later. So probably we can talk to you.
Oh, that's great.
No, I will talk. Thanks.
Okay, and then let's thank Dimos again.
Thank you. Thank you.
Hacemos un receso de 1 hora y media. Volvemos. Bueno, nos vemos a las 3:30. Saca la cuenta. Sí, pues.